We have a tool, but we don't really have an application for it yet. So we know that we've got these functions that look like f of t is equal to the sum from n equals minus n to n of cn e to the 2 pi I n t. And we know that cn is equal to the conjugate of c minus n, and we know that the magnitudes are the same. What we don't know yet is how we can use this idea to model periodic functions. And we also don't know how to compute the coefficients if we can. So the first thing we'll look at is how to compute the coefficients. And then once we figure out how to compute them, then we'll start thinking about how to show that any periodic function can be written this way. But for the next portion of our conversation, let's just assume that I have some function f, and that f can be written. So this is an assumption that we're going to make. We're going to assume that f can be written in the form f of t is equal to the sum from n equals minus big N to positive big N of cn e to the 2 pi I n t. And the big question is, how do we find the cn? In the case of the Legendre polynomials, we had that really neat integral formula that we could use because the Legendre polynomials were an orthogonal basis for the space of functions that we were working in, and so we could just use the vector projection formula. So that's actually going to turn out to be true in this case as well. But first we should see how Fourier himself did it, because they weren't working with the machinery of linear algebra, and so they didn't use these sort of vector projection ideas to come up with integral formulas for the Fourier coefficients, or the coefficients of this approximation. So we're going to look at the algebra that makes this happen. So what are the unknowns in this equation? So the unknowns are the cn's. We have f of t, which is some function that we know. Let's just suppose we know the function. And on the other side, we have this generic sum where I don't know the cn's. So I want to compute, say, ck, the kth coefficient. And I've got this pile of information that I need to use to do it. How can I find it? Well, I could just pull it out. I mean, there's a term over here that looks like ck e to the 2 pi I k t. So one thing I could do is I could just pop that term out of the sum and isolate it. And if I did that, what I would get would be ck e to the 2 pi I k t is equal to the sum from n is equal to minus n to capital N of all the rest of the terms. So here n is no longer equal to k, because I pulled that term out and stuck it over here. And the negative attached to it, plus f of t. That's just algebra. Popped out the term, stuck it on the other side of the equality, moved the f over, and this is the expression that you get. Okay, well now what? I still have ck isolated. So maybe now what I can do is I can take this entire thing and I could multiply it by e to the minus 2 pi I k t. Well, what does that get you? Well, it's going to cancel this one, and it's actually going to go inside the sum and affect all of these. So what do we get? ck is equal to the sum from n is equal to minus n to n not equal to k, of now cn e to the 2 pi I n minus k t plus f of t times e to the minus 2 pi I k t. So at least I've solved for c. So I've isolated the ck, but I don't have any more algebra that I can do because there's just too many unknowns running around the equation. And so this is where Fourier threw a Hail Mary. And when you're looking at an expression and you really want to be able to work with it, but you don't know what to do, one idea that you might have would just be to try to integrate it. And so what Fourier did was he took this equation and he integrated it. So Fourier's trick was to integrate both sides. And the first thing you can do is notice that ck is equal to the integral of ck dt from 0 to 1. That's a thing that is true. That's still equal to ck. So you could actually rewrite the thing you're solving for as an integral from 0 to 1 without changing anything. On the left-hand side, what you're going to get is the integral of this sum n not equal to k. And then there's actually also going to be an integral from 0 to 1 of f of t e to the minus 2 pi I k t dt. And what we want to concentrate on is this term right here. So I'm going to put the integral inside, and that's legal. And I'm just going to look at the integrals of this function right here. So here's where we are. I know that I've got f of t is being approximated by something that looks like this. And I want to compute the coefficient ck. And where we are right now is that ck is equal to the integral from 0 to 1 of f of t times e to the minus 2 pi I k t dt minus the sum from n is equal to minus n to n of cn e to the 2 pi I n minus k t, and then n was not equal to k right here. Oh, then there's an integral from 0 to 1 of this dt. Okay, so I took my original equation, I integrated both sides, and this is what I've arrived at. So let's look at this integral. So the CNs themselves don't actually matter because they're constant, so we can just pull it out, right? So there's a CN that we can pull out front of the integral. And now what happens with this? So the integral of an exponential with complex exponent is the same as the integral of a exponential with a real coefficient. Remember that the integral of e to the ax is equal to e to the ax divided by a. Same rule applies here. So now write down the integral, and what you get is Cn times 1 over 2 pi I n minus k, there's the constant, times e to the 2 pi I n minus k t, evaluated from 0 to 1. This makes sense because n is never equal to k, and so that's not a 0 over there, so you're not dividing by 0. If you put in 0 and 1, what you get is Cn times 1 over 2 pi I n minus k times e to the 2 pi I n minus k minus e to the 0. And that thing right there, remember that we're thinking about the unit circle, right? E to the 0 is equal to 1 because that's the same thing as the cosine of 0. E to the 2 pi I represents an angle where you've rotated all the way back to the original angle again. And you're multiplying it by some constant, n minus k, which is an integer. So n minus k just tells you how many times you've gone around the circle exactly all the way around. So e to the 2 pi I times any integer is also equal to 1. So this is 1 minus 1. And so this entire integral is nothing. So all of these terms here, all of these cancel away completely. And what you're left with in the end is that ck is equal to the integral from 0 to 1 of f of t e to the minus 2 pi I k t dt. This is the computation formula for Fourier coefficients. This is an enormously important computational formula. There is a linear algebra way of looking at this, and once we know that the complex exponentials are an orthogonal basis for a space of functions, then we'll be able to rewrite this in terms of a vector projection formula. But for now, this is the way this is typically introduced in engineering and applied science courses. And it's a very natural thing to have wanted to do. If we start with an f and we want to figure out ck, and I didn't know anything about crazy infinite dimensional spaces of vectors, and Fourier didn't, and you really want to find these coefficients, this is the way to do it. So what have we actually done here? This is where we are right now. If f is equal to the sum from n is equal to minus n to n of Cn e to the 2 pi I n t. So if that can be done, if f has a finite Fourier representation, then the coefficient ck can be gotten as the integrals from 0 to 1 of f of t e to the 2 pi I n 2 pi I k t. So the kth coefficient is computed this way. Okay. Now, really, I also get all of the c or the negative values of k for free, because remember that c minus k is just equal to the conjugation of ck. So once I have ck, I automatically get all of the negative coefficients as well. So I only need to compute half of the coefficients in the series to understand all of it. Now, there is a special notation for the Fourier coefficients that we're going to pick out because the Fourier coefficients are so important. In fact, you can completely understand a function that's periodic in terms of their Fourier coefficients. So we write that as f hat of k is equal to ck, which is the integral from 0 to 1 of f of t e to the 2 pi I k t dt. And those guys right there are super important. Now, the reason we're using function notation for this f hat is that we're going to be thinking about the process of finding coefficients as a function itself. So what we haven't done at this point is show when f can be approximated with a Fourier series. In fact, we don't know that periodic functions can be expressed this way yet. And that's going to be the subject of the next big part of our conversation, is going to be looking at when functions actually do have approximations as finite Fourier series and when they can actually be written as, say, infinite Fourier series. The last thing that I want to talk about in this video is the idea of finding the Fourier coefficients as a function. So if we had f of t is equal to the sum from n is equal to minus n to n of Cn e to the 2 pi I n t, we can think of the related function f hat of n as being equal to the nth coefficient. So the coefficients are so important that we're going to think of a function that takes in an integer and spits out the nth Fourier coefficient. Nth Fourier coefficient. And we just define that to be the function integral from 0 to 1 of f of t e to the 2 pi I negative 2 pi I n t dt. So f hat is our first example of something called a transform of a function. So this is called a transform. And it's called a transform because it takes f and it turns it into a different function. The original function f took in a real number, some sort of time, and it spit out a real number. And the number that came out was an amplitude, right? Because f is just some periodic signal, right? That's f. You give me a time, and it spits out some kind of amplitude. F hat, the function that gives you the coefficients, well, f hat takes integers in, and the integers are frequencies. And for a given frequency, what f produces is a complex number. And that complex number contains information about the magnitude of a given frequency and the phase shift. And since f is a function defined on the integers, what it produces is something that looks like a bar chart. And you've seen these before, for example, on your stereo. So in a follow-up video to this with some examples, I'm going to show you how f hat can be used to write what's called a spectrograph. So the graph of f hat ends up looking something like this. So you think about it as having inputs at 1 hertz and 2 hertz and 3 hertz and so on. And what the graph looks like is a series of bars that tell you the presence and relative amplitude of each of those frequencies in the original f. So f can be used to understand how the signal travels through time, and f hat can be used to understand how all the pieces of f are behaving. All right. So all of this stuff is the core of something called Fourier analysis, or if you like, frequency analysis. And the idea that f and f hat are related to each other, where they both give information about the other, and really that they're equivalent. They're equivalent functions. You can transform from one to the other back and forth. If you know what all of the relative frequencies and phase shifts of the harmonics that exist in a particular periodic function are, you can just reconstruct the function by multiplying by the appropriate harmonics. If you have the signal, you can use the computational formula to figure out what the f hat function must have been. So we're going to do some examples of this in the follow-up video of the application of this, but the ideas that we've discussed here are the heart of Fourier analysis, signal analysis. And the last thing that we have to do is talk about when we can actually do this. What functions f have the property that they have a Fourier series representation? And then we're also going to show that this is much easier if you think about it as a basis of functions inside of a vector space, an infinite dimensional vector space. And then all of the machinery that we did with the integration just turns into the dot product formula that we've already used in the Legendre case and in the Bessel case. Okay, so this really is the secret language of modern science. And so like drill down in here, read along in the book, and make sure you've got a firm grasp of what's happening before we move on. All right, I'll talk to you guys later.